So this is a question about transition metals and also the aqueous reactions of complexes. It's 12 marks in total. It runs all the way from A to G. So pause on each section, see how you do, and then review. Here's part A, part B, part C, part D, part E, and finally parts F and G. So now let's start to go through. We have got, in the first instance, a reaction between hexaaqua 3 ions reacting with an excess of HCl, and you're told it's a ligand substitution reaction. Now, for the equation, you first of all have to remember what the hexaaqua ion 3 complex looks like. It's an Fe surrounded by 6 waters. The charge on the ion is +3, and because the charge on a water ligand is 0, the overall charge on the complex is +3. Now we're adding hydrochloric acid, but you will need to remember that that's the chloro ligand. Now when we actually make our product, we will make FeCl4. The next part of the question actually explains why, but you have to remember that you can only fit 4 chlorine ligands around the central metal ion. Now you've also got to remember that the overall charge is the sum of the charges. I've got 4 Cl minuses here with 1 Fe plus 3, so my overall charge is -1. And because the Cl minus has substituted the other ligands, I've also got 6 H2O. So there's a lot to consider when you're putting that together. Now when we move on to part B, we talk about why we see the change in the shape. We've gone from octahedral to tetrahedral, and it's actually a really straightforward answer. Chloroligands are bigger, and because they're bigger, you can only fit 4 of them around the central metal ion, and that's always true. In general, you're going to see complexes with a coordination number of 6. 2 notable anomalies are chloro, where chloro complexes will be tetrahedral, or, superseding that, if silver is your central metal ion, they will be linear with a bond angle of 180. So moving on to part C, and you're being asked to draw the structure of the iron 2 complex formed, showing its charge. Now, I would always recommend when you're drawing a complex, start with the central ion and draw the spokes coming out. This is octahedral, so we do have 6. Now, we know it's the ends that are going to connect, so that has to be reflected in what you draw. So I'm now going to add my 3 bidentate ligands on. And I've been very, very careful that it's the N in the NH2 that's at the end of the bond. The rest of it has been done skeletally. Now, that obviously has got to go into square brackets, and that's because it's a complex and that's what we generally do, but also because we want to represent the charge. And the charge on the ion is +2. There's no charge on our ligand, so the overall charge is also +2. And the breakdown of marks here is 1 for the correctly drawn complex and 1 for correctly identifying the charge on the ion. Moving on to part D, we have hexaaqua ion 2 ions once again, still reacting in that same way, and we want to know what the change in entropy will be. Now you can think about what's changing here, and it's a theme that's gone through the whole question. When we began, we had 3 ligands and 1 complex, so that's 4 moles in total. As those 3 ligands have substituted the water, we've been left with 1 complex and 6 water molecules. So we've gone from 4 moles to 7 moles. Entropy is a measure of disorder. So if I have more molecules, there is an increase in disorder, there is an increase in entropy, so the entropy value is positive. Moving on to part E, and we've got here a really important equation that's going to come up in redox titrations, and actually the redox titration calculation that follows does rely on this being done correctly. So when you're doing the ionic equations, I'm going to break it down to the half equations and build them up as a bit of a reminder of the rules of redox. I know, or I need to know, that my manganate 7 ions are reduced to Mn+2. I'm then going to follow the rules. I can balance the species with a variable oxidation state. In this case, that's manganese, already balanced. I am going to balance the oxygens by adding water, so I've added 4 waters on the right-hand side. I'm going to balance the hydrogens by adding H+. I need H plus 8 of those on the left. And finally, I balance charge by adding electrons. So I've got 5 E- on the left-hand side. Now, if I do the same with the Fe2+, going to Fe3+, again, you will be expected to know that's the change happening in these titurations. My first rule, the iron is already balanced. There are no oxygens to balance for rule 2. There are no hydrogens to balance for rule 3, so I'm going to balance charge by adding electrons. Now, if I'm going to combine these half equations, I need to end up with no electrons left, so they need to be cancelled out as spectators. If I take a look, I've got 5 electrons on the left in the first half equation, only 1 on the right on the second equation. So I'm going to multiply the whole of the second equation by 5. Now what I can then do is combine everything on the left hand side to go on the left of my full equation and everything on the right hand side to go on the right of my full equation. And this is the equation that we end up with. Going to move on to F, and we have got here quite a lot of information. The 1,980 milligrams of iron tablets, they're not all iron, and the purpose is working out what percentage of that is actually iron. It's in dilute sulfuric acid. That prevents the oxidation of iron 2 to iron 3 before the titration takes place. We've got a concentration and volume of potassium manganate 7, and we're doing a titration, so let's draw out a titration table. I've got my C, V, N, and ratio. C being concentration, V volume, N number of moles. Now I've got 2 species I'm interested in. One is the MnO4- ions and one is the Fe+2 ions. The 2 things that we had in the equation that you put together in part E. At this point I can go through my data and substitute what I know into the table. So I was given a concentration of MnO4-. I was also given a volume, but in centimetres cubed, so I need to convert that to decimeters cubed. Once I've got C and V, I can multiply those together, and that will give me N. So I've got 6.5 by 10 to the minus 4 moles of MnO4-. But I'm more interested in the iron for the purpose of the question. Now again, we go back to that previous question. The ratio of MnO4- to Fe+2 is 1 to 5. So if I want to know the moles of Fe2+ that I was titrating against, I'm going to multiply 6.5 by 10 to the minus 4 by 5, giving me the value 3.25 by 10 to the minus 3. And here we hit a bit of a sticking point because I don't have a concentration or a volume. But I want to know mass, and I can find the MR of iron. So I can put the 55.8, the atomic mass I should say, AR of iron into the table, and from there I can calculate my mass as 0.181 grams. Now we know the total mass of the tablet was 1,980 milligrams. So I'm going to convert my 0.181 grams into milligrams, and I'm going to work that out as a percentage of the 1,980. And that takes me to the overall value of 9.14%. And finally, for part G, the colour change for this, which in manganate 7 will always be the same. It's an auto indicator. Manganate 7 is a deep purple colour, but the end point in this titration is when you first have manganate 7 that's not reduced. So what we actually see is a pale pink tinge in our solution.